Question 5. Gotta catch 'em all. Or gotta catch a lot of them, or try and catch as many of them as we can. So this is going to be an approximation algorithm question. So you can go ahead and read the intro, but the idea is that we have M trainers, and we're going to choose a subset K of them to be on our team. And we want to choose these K trainers in order to maximize the number of distinct Pokemon that we have on our team. In order to do this, we're going to give a greedy algorithm, and then we want to show how good of an approximation that greedy algorithm is, and eventually show that it's a 1 minus 1 over e approximation algorithm. So the greedy algorithm basically just goes through, keeps track of the trainers, keeps track of the Pokemon, and keeps adding trainers. And since you get a total of K trainers, it runs K times, and just greedily picks at that moment which trainer will give you the most Pokemon. And we'll do a couple examples of this to get comfortable with how the algorithm is working. We ultimately want to show that this algorithm runs in polytime. Then we want to show this thing, which has a whole bunch of notation, which we'll go through. But after we prove this inequality, it will help us show that the algorithm is a 1 minus 1 over e approximation. So let's first do a little example with this algorithm to get comfortable with it. To make it more concrete, let's set m equal to 3. So this would mean that we have 3 trainers, Jesse, James, and Misty, and each one of them has a certain set of Pokemon. So let's say these are their Pokemon. And let's set k equal to 2. So in other words, we want to choose 2 of them to be on our team. At first glance, since we're trying to maximize the number of distinct Pokemon, it might make sense to immediately say, okay, I want to choose Jesse and James because they have the most number of Pokemon. But this actually would not be the best solution because they have a lot of overlap between which Pokemon they have. So another way to visualize this would be as a Venn diagram. So in our algorithm, let's say we break ties arbitrarily. So at the very start, it makes sense that we either want to choose Jesse or James because both of them could give us 4 new Pokemon. And let's say we break ties arbitrarily and we pick Jesse. At this point, we just pick the trainer with the most new Pokemon. After picking Jesse, James only gives us 1 new Pokemon, but Misty would actually give us 2 new Pokemon. So we should end up choosing Misty, and that would be our final team of 2. The important thing to note was that even though James had more Pokemon overall in comparison to Misty, after we picked Jesse, we didn't want to pick James because he would have only added 1 new, she would have added 2 new Pokemon. And running through the algorithm, we can kind of see that this took us k iterations. So we had to look through 2 times to select our final team of 2. And at each iteration, we just kept looking through all of the remaining trainers and seeing which one would give us the new Pokemon. We saw James would give us 1 new, Misty would give us 2 new, and then we just increment our sets so we can keep track of how many Pokemon and who our trainers are. Hopefully after seeing this, it makes sense that the algorithm is polytime because we iterate k times, and each time we go through all the trainers to find the argmax, and we just keep a running set of which Pokemon and which trainers we have. So you can formalize that, but it should make sense that the algorithm is running in polytime. It's not doing something like try out all possible combinations of trainers or something like that, which would get us into exponential time. Okay, now for part 2. So part 2 has a lot of notation, so before we try proving this inequality, let's first make sure that we're comfortable with what each one of these symbols means. So T star is the optimum solution. U star is the union of all of the Pokemon from each one of the trainers from the optimal solution. So this is the optimal trainers. These are the optimal Pokemon you get after choosing the optimal trainers. But UI is not going to be the optimal, but rather the set under our algorithm, which may or may not actually end up with the optimal set of Pokemon. It's going to be the set of Pokemon after the ith iteration of the loop. So now we want to prove that the difference between the optimal, or the size of the optimal solution, and the size of how many we got so far is going to be bounded by this fraction of the optimal. So let's see each one of these terms in a larger example. So in this example, we have 11 Pokemon and 5 trainers, so M equals 5. And we ultimately want to select a team of 4. You can go through this and try it yourself, and you'll notice that the optimal solution is going to be these 4. Ash, Bee, Gary, and Dawn, and by choosing these 4, you'll actually be able to cover all 11 of the Pokemon, and you actually did catch them all. Now let's see what happens when we run our algorithm. So that's T star and U star. Let's take a look at what UI looks like. So our algorithm, the first thing it's going to do is right now we have a total of, you can think of it as U sub 0. We have 0 Pokemon so far. And we're looking at which trainer would give us the most new Pokemon. And we break ties arbitrarily. So in the first iteration, we see that Ash would give us 4, Bee would also give us 4, Serena would give us 4, Gary gives us 3, and Dawn gives us 1. So it's really down to Ash, Bee, or Serena, and since we break ties arbitrarily, let's say I pick Ash, and I get 4 Pokemon. Now I just need to do 3 more iterations to figure out who to select next. After selecting Ash, since we have these 4, if we look at Bee, she only adds 1, 2, 3 new Pokemon, but Serena would add 4 new Pokemon, Gary would add 3, and Dawn would add 1. So at this point, it makes sense to choose Serena because she adds the most new Pokemon compared to what we had before. After we add both Ash and Serena, we'll notice that Bee, Gary, and Dawn would each give us just 1 new Pokemon. So at this point, regardless of how we break ties, because we only have room for 2 other trainers on our team, and Bee, Gary, and Dawn would each add 1 unique Pokemon that no one else has added or could add, we're always going to end up missing one. So no matter how we break ties, in this case, I'm just going to go ahead and let's say I pick Gary and then pick Dawn. I'm always going to be missing one. So in this case, I'm missing this Pokemon here. So the important thing first to notice is these sets U1, U2, U3, we're always increasing. So that's what each one of these is. So that means this quantity right here, the optimal minus the size of UI, as I increases, this quantity decreases. And the other thing to notice is that we didn't necessarily reach the optimal solution by using our greedy algorithm. So the optimal solution was able to catch all 11, but our algorithm was stuck at just 10. And the reason for that is because it made greedy choices, which meant it made choices that were optimal locally, but overall might not lead to the optimal solution. So they were only the best choice to make locally. So that would be after we selected Ash and we were looking for the next person to pick. Locally, Serena did give us the most Pokemon. She gave 4 when everyone else gave 3 or less. But overall, that's actually not the best choice because all of the Pokemon she could add were already covered by other players, so she's not actually adding anything more, and we end up missing all 11 Pokemon. Okay, with that intuition in mind, let's go ahead and get started on part 2. So first things first, we can maybe give ourselves some notation to make this easier. We want to prove this inequality for all of the iterations for all values of I, where I goes up from 1 to k. Let's call this quantity Ri. And since we want to show some inequality holds true for I all the way from 1 to k, a good proof strategy might be induction. Of course, we could do this induction for all natural numbers, so we want to show this inequality holds for all natural numbers, and in our algorithm, even though we only use it for I from 1 to k, we can just prove a stronger claim and prove it for all natural numbers and prove our claim as well. So getting started with induction to show that this inequality holds true, we can start off with our base case. In this case, our base case would be when I is equal to 0. And notice that when I is equal to 0, this corresponds to like before any iterations have run. At the very start, you don't have any Pokemon, you just have the empty set. So R0 is going to be the optimal minus nothing at all. So we still have the optimal left, so that's the left-hand side. And for the right-hand side, I is 0, so this whole thing just becomes 1, and that's also equal to the optimal. So the size of the optimal is less than or equal to the size of the optimal, so we're done. The base case checks out. Our induction hypothesis is going to be your standard weak induction hypothesis. We're going to assume that the inequality is true for I minus 1, and we want to show that it holds true for I. For our induction step, this is where things get a little bit more interesting. So in order to show that this inequality holds for I, given that it holds for I minus 1, we have to consider where we're picking from at iteration I. So at iteration I, the Pokemon that we don't have from the optimal solution is going to be the optimal solution set minus all the Pokemon we have so far. So this is the set we're looking at. Let's go ahead and give a quantity to the size of this set. Let's call it C. And the reason we're defining this is because this set Ci, this is different from Ri. Ri is the difference in the sizes between the optimal and what we have so far, while Ci is the size of the difference between the optimal and what we have so far. So it's a little tricky, but try out some examples and get comfortable with these quantities. So let's see one example right now. We'll notice that Ci is always going to be greater than or equal to Ri. This inequality always holds. And you can kind of see that by running a couple of examples just to get an intuition for it. But notice that Ci is always going to be the size of this part, which is the part of the optimal solution that you haven't covered. These are which Pokemon of the optimal you haven't gotten yet. While Ri is always going to be smaller, since it's going to be what the optimal solution is minus the size of Ui. So it subtracts anything that was in this section, which is always going to be either 0 or greater than 0. So Ri is always going to be, the biggest it can be is Ci. That would be when this section right here on the right is empty. And the more Pokemon that are in this section, the smaller Ri is in comparison to Ci. So once we have this inequality, this actually helps us with our proof because it's easier to bound how Ci is changing rather than how Ri is changing. In particular, if we consider what the optimal solution Ui is made up of, it is made up of K Pokemon sets from each of the K trainers. And notice that at least one of those trainers must cover at least a 1 over K fraction of this set right here, which is why we define Ci. So the way to like prove that to yourself is that if you assume for the sake of contradiction that none of the trainers covered at least this much. So in other words, all of the trainers covered less than a 1 over K fraction of this subset, then you wouldn't ever be able to cover all of U star, which is a contradiction because we know that the optimal solution uses K sets to cover all of U star. Once we have this in mind, we know that our algorithm is greedy, which means that each iteration, the trainer that we pick is going to cover at least as much as this. We know that one of the K sets covers this much. The one that we pick is going to be the maximum, so it covers this much or more. So the trainer we pick is always going to cover this fraction or more, which means, like we said before, Ri is always decreasing. Now we can bound it by how much it's decreasing. So Ri is going to be less than or equal to Ri minus 1, so from the previous iteration, minus at least this much, because that's how much is covered by one of the trainers. And since we know that Ri is less than or equal to Ci for all I, we can go ahead and replace this with Ri. And now we have an inequality just in terms of R, which means we can factor, and then we can go ahead and apply our induction hypothesis on Ri minus 1. And once we apply our induction hypothesis, we can simplify and get what we wanted to show. So through this induction, we prove this inequality. So the whole point of doing all of this work and proving this inequality was actually so that we could show that our greedy algorithm is an approximation algorithm for finding the optimal set of trainers. And now we're going to show how good of an approximation it is. So from what we learned from part 2 was this inequality. And once we go all the way to the last iteration, which is the kth iteration, just plugging in k for I, we get this inequality. So we can use this inequality to show that we have a 1 minus 1 over epsilon approximation. So in other words, the set that we output, which is U sub k, is going to be at least 1 minus 1 over k as big as the optimal solution. So we know that we're given this inequality, and since we want to bound, we also have this inequality and we want to bound this, it would make sense to pick x equal to negative 1 over k. So if we choose x equal to that, this inequality, just plugging it in, becomes this. And doing some math, moving things around, it simplifies to this. And this is useful because we can plug it into the inequality we get from part 2, bounding this fraction right here by 1 over e. So just replacing this whole fraction with 1 over e, we get this. And remember, we defined rk to be the difference in sizes between the optimal solution u star and our solution at the kth iteration, which is our final solution. So plugging in our definition of rk, we get this, and then moving things around, just some algebraic manipulation, we get exactly what we wanted to show, which is our algorithm's output is at least 1 minus 1 over e fraction of the optimal solution, which is exactly what it means to be a 1 minus 1 over e approximation, which is what we wanted to show, and we're all done.